Hello, my name is Stan Kriventsov. I work here on the 12th floor for Bioconscious Tech doing blood glucose predictions for diabetics. I only have one monitor, horizontal. I used to be a professional online poker player. I played up to like 24 tables at the time. So maybe that's when I needed all of those extra monitors, but I always just had one. Also, I do some Kaggle competitions. This was actually my second Kaggle competition that I participated in. The first one I did it last spring, and then I did a presentation after that Kaggle competition, and a guy came before the presentation, and I gave him my resume because I was looking for a job, and that's how I got hired. So actually giving those presentations is a good way to look for a job in case like there are a lot of people you're basically exposing yourself to. And so if you're looking for a job, maybe you could consider making one of those presentations in the future. So this was the second Kaggle competition that I participated in, as I said, because in December I had a little bit extra time and I figured this looked simple enough. It's actually a little bit different from standard Kaggle competitions because it's not so much a machine learning competition. It's more of like a math, algorithms, and programming competition. And they actually have it every year with some twists. The name of the competition is Travel in Santa 2018 Prime Paths. And it ended a couple of weeks ago, January 10th. So here I summarized the problem. So basically, it's a variation of the standard travel and salesman problem, where you have to go from city 0 to all of the cities, visiting each city just once, and then coming back to city 0. And you have to find the path that is the shortest in terms of visiting all of those cities. Here, there was a little bit of a twist that the length of every 10th step was increased by 10% if this step didn't originate from a city with a prime ID number. It's a little bit random, but I mean, this is like a fun competition that they have at the end of the year, so this doesn't necessarily have any practical meaning. But and the cities are taken from pixels in the picture on the previous page, this one here. And basically, all of the data for this competition was in this format here. So basically, city ID for cities from 0 to 197,768, and the X and Y coordinates. And that's pretty much all we needed to know to participate. Here, I plotted the non-prime and prime locations of the city and also the city 0 there. And as you can see, those prime locations, they're distributed pretty evenly. So in theory, it could be possible to get a lot of them in those 10th positions so that you don't pay the extra 10% penalty. But I don't think anyone, I mean, like at least none of the top winners, I'm pretty sure, got any paths that had all of the prime cities in those 10th positions, because that would probably be quite suboptimal from that, like the general length standpoint. And this is what the sample path looks like. I used my own submission to generate that. And as you can see, there is a lot of like kind of wiggles, and it's maybe not quite what I would think it would look like. But it's pretty interesting. It kind of looks like fractals or something if you look at it. And there is a reason why it would always look like that when you're solving a travel salesman problem. Yes?
Sorry, I may have missed this one right at the door. First, why is there a reindeer on the...
Because it's a Travel in Santa competition.
Oh. Okay. Is this... Can you describe what the lines are? Is this like one place to one place?
This is the path from city 0, which is located where the blue dot is. I'm not sure if you can see the blue dot there or not. Yeah, so it goes through all of those pixels and comes back to city 0.
Okay.
And like the line basically just follows that path. And in some places you can't really tell that it's a line because there are so many pixels. Like in that tree, for example, on the right.
So in the open area, in the white area, the reason why they're not all straight lines is because there's prime cities in there that.
The reason why they're not straight lines is because not every point in the picture contains a city. So you have to go from city 1 to city 2 on your path, city 3 and such. So since there is almost 200,000 cities there, basically the parts of the lines that are not straight, it just means that there are multiple cities there. So it goes to, there is one short straight line, there is another short straight line, and so on. But when you look at it with this resolution, then they look like they're not straight.
Question, does the path ever cross itself?
It's a complicated question. I mean, this path probably at some point, I mean, in general, it shouldn't. Like, if it was like a travel and salesman problem without the 10% prime penalty, then it should never cross itself. And there is a reason, I'll tell you later why. With the prime penalty, I think there is a good chance that there might be some point somewhere where it crosses itself. It's fairly unlikely because, I mean, there is a simple way to get a better path if you have a crossing of, if you have a crossing somewhere. There's a simple way to get a better path by doing something that is called a KOpt. And I'll talk about that. But with the prime penalty, it's possible, yes. Yes?
Okay, so if you... so if you represent this... okay, if you represent this problem as a graph, so it will be fully connected graph with all edges adjacent to prime vertices more expensive, right?
Not quite. Well, first of all, less expensive. Second, it's only true if those prime vertices are in those like every 10th position. And third, it will only be the outgoing vertex. I mean, like one outgoing edge, one of those two outgoing edges that goes from the 10th position to the 11th, I mean, actually 9th to 10th position. Any other questions? All right, let's move on then. Okay, so I decided to start with the final leaderboard. Yes?
Was the picture your submission by itself?
Well, it's the picture generated based on my submission. The submission itself was just a list of numbers. Like, let's say we start at 0, then the first is like city number 44073, the second is city number 127025, and so on, listing all of those numbers from 1 to 197,768 in the order of the path.
So which tool did you use to generate this, if I may ask?
Just Python, like pyplot. Basically, just from generate a straight line from point 1 to point 2, then from point 2 to point 3, and so on.
So the question was framed in such a way that the path actually picturizes this picture.
Yes, as I said, this picture was used to create the problem. So basically, every pixel in this picture was like the coordinates of which pixel were calculated and then just put into that CSV file. What do you mean every black pixel? It's not like
every black pixel, because every single.
Well, not like white pixels. Yeah, like if it's black and white, yeah, then every black pixel, yes.
I mean, I don't believe it's just the black pixels because there are like the quadrants on the left bottom side, which is like just white, and it still has a path. I mean, yes, there are cities there, but I'm saying like that's not a black pixel in the picture. Oh,
Well, here is the original picture.
oh, okay, yeah, yeah.
Those are like snowflakes, I think. Right. So this is the final leaderboard. As you can see, the scores are somewhat close, but not like extremely close to each other. The first place is that team actually, it was in the first place for most of the competition, and it was quite a bit away from the second place, and the second place was quite a bit away from the third place for most of the competition. And I also put those scores for, if you just take all cities from in original order, if you go like from 1 to 2, from 2 to 3, and so on, then you get a really horrible score, which is like 400 times or something, 300 times larger, because you'd be jumping all over the map instead of going to cities that are close. If you use the nearest neighbor algorithm, you get a much better score. It's still much worse than what the leaders got, obviously, but it's only like 1,800,000 instead of 1,500,000. So actually, many algorithms, they started out using the nearest neighbor as the first approximation, and then they improved upon that. Okay, so in order for you to understand what the leaders did, I'll do a little bit of research review here. So here is the history of the travel and salesman problem in like very brief points here. So although it has been mentioned in some previous research, but it's like the mathematicians started to study it around 1930s. In 1970s, it was proven to be NP hard, so you cannot solve it in polynomial time. And when the number of cities grows pretty large, it's actually very hard to solve even with modern computers. Like it's impossible, like for this problem where it's 200,000 cities, it's impossible to solve it exactly, or at least like no one has figured out a way to do it yet. The largest travel and salesman problem solved exactly is about 86,000 cities. So to solve those larger problems, there are many approximate methods that are called heuristics, often due to the nature of them. Basically, the way, yes?
What do you mean solving it exactly? Proving that it's the best solution,
Yes.
Or by enumeration?
Yes, proving that it's the best solution. Yes.
Without enumerating it, or?
What do you mean without enumerating?
Like you could enumerate all permutations.
No, not using permutations,
Okay.
obviously. But I'm not sure exactly how they proved that it's the best solution, but I mean, somehow they did. Yeah, I didn't research exactly how they proved that this 80. There is maybe something like with upper bound estimations and such. Yeah, I'm not sure how they proved it. So basically, the approximate solvers, the way they work, basically you start with some sort of a path, and like maybe nearest neighbor or something, then you gradually improve it by making small changes in like some small parts. And that's what I'll be talking about, how to make those changes. And modern TSP solvers, they're actually pretty good. They can usually find solutions within less than 1% from the optimal score. Once again, the way they do it is they estimate some bounds and see what the optimal score should be. Okay, so the best existing travel and salesman problem solvers are LKH, that was written by Kjeld Helsgaard from Denmark, and Concord by William Cook. And those are the two guys that created the first place team. So yeah, once they entered the competition, basically the rest of the competition didn't have a lot of chance, although the second place team actually gave them a good run for the money, but it was never like super close. So yeah, that was interesting. I mean, like in many Kaggle competitions, I guess there are some people who specialize in that area, but to have like two leading world-class experts doing the competition, yeah, that's a little bit unusual. Okay, so basically here is the basic idea that most people used in their competitions, in generating their submission. So they first used existing travel and salesman problem solvers such as LKH. LKH was especially useful in terms of generating good solutions here. And then they tried to rearrange the route to move prime cities into those 10-step locations, or rearrange it in some other way. But usually what it amounted to is just moving those prime cities there, because otherwise it would be pretty well optimized with the TSP solvers as it is. So the prime penalty was fairly small. It was about 1% of total tour length. And actually at the beginning of the competition, some people complained that it should have been bigger, because otherwise people would just use the standard solvers and just get into prizes, but that was not really the case. Yeah, like if you just took the best non-optimized solution, you would probably get somewhere in the top like 30 or 40%, but definitely not anywhere close to the medals in the competition. I guess most of you guys sort of know how that medal system works on Kaggle. So you, like for the first like 10 spots, maybe you get the gold medal, and then for the first 5%, I guess you get the silver medal, and for the top 10%, you get the bronze medal. And also, like in this competition, there was a $25,000 prize fund, which went to the first 3 places. Yeah, so as I said, like given how good the existing solvers are, it makes sense to just go with that solution and then try to optimize it instead of trying to generate something from scratch. Although it would be possible to modify the existing C++ code, usually most of those solvers use C++, to include the penalty right away. And to a certain extent, that's what the first place team did, because they wrote that code originally, so it was easier for them. But all of that code is open source, so anyone with knowledge of C++ could have done it. Okay, so and here I just sort of give some information on, yes?
So if there wasn't that twist with the prime numbers, would everyone just have used the open source solver and gotten the same
Right,
score?
yeah. Without that twist, it would not be a very interesting problem, because then it would be a competition of who has the most powerful computer. Although, I mean, maybe like, let's say those like the first place team, maybe they would have come up with some tricks that they haven't like included in their software originally. I don't know, like they always might have some more advanced versions, you never know, but.
And so you say mathematically they're within 1% of the optimal solution? Is that what it is?
Right. Usually those solvers generate solutions that are pretty close to the optimal solution, and they have some ways to prove it using like bounds and like mathematics.
So the optimal solution is known?
No, it's not known. That's what I'm saying. It's not known, but they can estimate where it is. Yes, Ken.
So I didn't understand how these penalties work. So can you just describe it a bit?
How the penalty works?
Yeah, I keep confusing
about
it.
So basically, you go like from, let's say you just keep the cities in their original order. You go from city 0 to city 1, from city 1 to city 2, city 2 to city 3, and so on. And you are calculating the length as the Euclidean distance between those cities based on the coordinates. Once you get to the city 9, then the step from city 9 to city 10 will be your 10th step. So since 9 is not a prime number, the length of that step, the Euclidean distance, will be multiplied by 1.1. So there will be an extra 10% added to it. If 9 were like, let's say when it gets to 19, 19 is a prime number. So from 19 to 20, it will not be multiplied by 1.1, that distance. So you want to have as many prime numbers as you can get into those spots, number 9, 19, 29, 39, and so on. Hope that clarifies the problem. So basically, if you don't optimize at all for primes, you should expect about 1,780 primes in those locations based on the number of primes. Just it's about 9% of all cities are prime cities. In my final solution, which was somewhat optimized, there was about 4,000 primes, about 20% instead of 9%. So there was a significant improvement in terms of getting the primes there. In the first place team's kernel solution, which is worse than their actual solution that they submitted, but they didn't release that solution that was submitted for first place. But the kernel solution had more than 5,000 primes, more than 26%. So I guess their actual solution would be around a little bit over 30% probably of all primes in those locations. So actually, that was pretty good. So now I'll go through different approaches that you can use for this problem. The first one, as I mentioned, is nearest neighbor. That's pretty fast to implement. You can run it in like several seconds if you have a good code. And it gives a decent initial solution, as I said, with a score of about 1,800,000 something. It's suboptimal even in terms of like without the prime penalty, it's quite suboptimal because basically when you are always looking for the nearest neighbor, at some point you'll just run out of nearest neighbors because you're not optimizing and you'll have to make some pretty big jumps there. Especially like at the end, usually like if you're always looking for a nearest neighbor, you're not gonna finish anywhere close to the starting point. It's possible to improve it, but the improvement is not so great. That was actually the first thing that I tried when I looked at this problem, because when I started working on this competition, I had no specific knowledge of the travel and salesman problem outside of the fact that it existed. Yeah, so the next thing that you can try is permutations. Basically, just try putting them in all possible orders and see which one results in the lowest path length. So the time cost is about n factorial for that because you have to try all of those permutations. So for the number of cities that we had in this problem, it would take about 10 to the power of 960,000. Which would not allow you to finish before the end of the competition. So yeah, that's not the great approach. If you have like a really fast computer that can somehow evaluate 10 to the 9th permutations per second, you need about a day for n equals 17 and about a year for n equals 19. So
what is n?
N is the number that you're trying to permutate over. So if you have a problem with, let's say, 17 cities, you can do it in about a day on a regular computer. You can prove, like you can just try all permutations and see which one would have the lowest path, the lowest path length. This is actually not a very smart way of doing it. There is a thing called a held-carp algorithm, which existed since about the 1960s, I think, or 50s, something like that, or early 70s maybe, which allows you, instead of O of n factorial, which allows you to do it in O of 2 to the power of n times n squared. And the way you do it is basically you're wasting a lot of time when you're trying all of the permutations. Because once you establish the correct order of the inner terms of a segment like that, let's say 10, 11, 12, 13, 14, 15, if you determine that 11, 12, 13, 14 is the optimal order for those, then as long as you have 10 on one side and 15 on the other side, it doesn't matter what you add on the right and on the left. The optimal order is not going to change. So the way, if you write that algorithm the way it is, you can save a lot of time not looking at all of those. You just start with smaller length paths and then you add more and more. But this algorithm, the problem with it is that it has to store all of those paths. So at some point you run into memory problems. Like I implemented that algorithm and I ran it at about n equals 24. You can do it in about a day, and n equals 24, n equals 25. But for n equals 24, you need about 50 megabytes. Is it megabytes, gigabytes of RAM? 50 gigabytes of RAM. For each consecutive n, like it doubles. Like for n equals 25, you need about 100 gigabytes of RAM. So yeah, like you can't go very far with that. Maybe, I mean, if you have like really a lot of RAM, you could go to n equals like 27, 28, something like that. But yeah. So permutations is a great approach for local optimization. So once you've generated the path that you think is good, it's good to like run those permutations with n equals like 24 or something, and just make sure that you cannot locally optimize it further anywhere. And usually if you haven't done it before, you get an improvement in this problem of about like 20, 30, 50 maybe points, but it's not a great improvement. So the next approach that is actually very important for solving this problem is the minimum spanning tree and the alpha nearness, which is used by all of those TSP solvers. A minimum spanning tree is a subset of the edges of a connected edge-weighted undirected graph. I just took the definition from Wikipedia, that connects all the vertices together without any cycles and with the minimum possible total edge weight. So basically, you're trying to create a tree that connects all of the vertices of your graph and has the minimum possible length. And it's much easier to find that the optimal closed path, because you can use this Prim's algorithm, which was discovered by Jarnik actually in the 1920s, but no one knew. And then it was rediscovered by Prim in 1957, I think. And then it was rediscovered by Dijkstra in 1959. But Dijkstra already had his own algorithm, so it's not called Dijkstra algorithm. It's called, it's usually called Prim's algorithm, but Jarnik actually was the one who invented it first. So basically, you start with an arbitrary vertex, and then you just add the shortest edge from that vertex within the tree to a vertex that is not in the tree yet. So it's not a very complicated algorithm. And the runtime of it is of m log n, so no factorials or exponentials here, so you can do it pretty easily. Why do you need this minimum spanning tree? Is because it allows you to calculate alpha nearness, which is important here. So for any two cities, the alpha nearness is the difference between the distance on the minimum spanning tree and the Euclidean distance. So if they're connected directly, it means that alpha nearness is 0, because the distance on the tree is the same as the Euclidean distance. But if they're not connected directly on the minimum spanning tree, then you have to go through some other points, and the distance on the tree will be greater than the Euclidean distance. So the points that are actually quite close in Euclidean distance, if they're far, if you have to go through a lot of other points on the minimum spanning tree to get from one to the other, then they'll have pretty high values of alpha nearness. And I showed the picture here, which demonstrates sort of the idea of this alpha nearness. Let's say you have this continent on the left where you have a lot of points, and you have a small island of points on the right. So if you only look for like nearest neighbor points, then the points on the continent will never find those points on the island, because they're too far compared to a lot of points that you have near on the continent. But the problem is, if you're creating a closed path, then sooner or later you'll have to get to those points on the island as well. So in order to do that, you have to include those in consideration as effectively the closest points to some of the points on the left there. That's why alpha nearness is pretty good for generating ideas of where you want to go next from this city, because sometimes it will not be the nearest neighbors. So, and actually I did that too. I generated the shortest path based on alpha nearness as opposed to nearest neighbor. And it actually turned out to be better. It's about 1700 instead of 1800. It's still not a great path, but yes.
We anyway need to finish it at the 0th city, right?
Yes, yes, we're coming back to city 0, yes.
Yeah, so it anyway needs to follow the alpha something you said, not the nearest neighbor, because like anyway the last city is going to be further away from.
Yes, that's what I said. If you use nearest neighbor, you'll likely end up somewhere very far from the starting city. So your last move will be, it could be like several. I mean, basically, like let's say it was about 5,000 by 2,000. So it's you'll be adding like several thousand to your total score, to the Euclidean distance, which would basically just this one step will basically knock you out of any kind of contention for prizes in the competition, because yeah, it will be huge. Yeah. Yes, Kenneth?
So did you implement the local scoring on your local system, or was the leaderboard what you used for?
Say it again. Did I implement what?
The scoring, like this.
Oh, the score, calculating the score?
Or did you use the leaderboard just to know what the scores is? Do you have a local?
No. I didn't use the leaderboard. I mean, that would be impossible to do. I mean, basically, you need to generate millions of solutions and evaluate them and see if they're better than your current solution or not, if you want to improve your solution. If you just try random improvements and do it on the leaderboard, you can only do it 10 times a day, so you'll never get anywhere. So yeah, it's not that hard to implement. I mean, basically, it's just the Euclidean distance with the 10% penalty. So I mean, like if you just want to write straightforward procedure to do that, it will probably do it like in a second or like something like that. But there is a way, like if you really optimize it, you can get it down to maybe like 10 milliseconds or even a bit faster than that. And I'll talk about optimization a little bit later there in the presentation. So you can, the reason I was talking about alpha nearness and all of that, so now we're getting to actually the methods that are used in most top TSP solvers. And the main method that is used is those KOpt heuristics. The basic idea is to replace some K edges of this path with K different edges and hope that the result will be an improvement. So basically, you try a whole bunch of those, and you see which ones improve your path. Obviously, to have a realistic chance at improvement, you have to use some sort of a smart algorithm on how to choose those edges. And obviously, like in a near optimal or optimal path, all of those cities that you're connecting should be reasonably close to each other in terms of either nearness or alpha nearness. So basically, you don't want to jump from one side of your picture to the other. So alpha nearness helps you choose the candidates. Like if you remove a certain edge, then where do you want to go from that city? So alpha nearness generates the candidates for you. You can go to that or that city where you have 0 or very low value of alpha nearness. So here I'm giving a simple example of a 2-opt where you're just replacing 2 edges. And that actually shows you what happens when you have when you have the path that crosses itself. So on the left, you have the path that crosses itself. And in case if there is no prime penalty, you can always improve it by doing like going from the left to the right. So you remove those 2 edges that cross each other, and you replace them with the other 2 that I drew there. And what happens essentially is you have to go through the same cities, but in the opposite order. So let's say if you had cities 1, 2, 3, 4, 5, 6, 7, 8, 9. Then now you go 1, 2, 7, 6, 5, 4, 3, 8, 9. So yeah, so this is a very simple move, which is a 2-opt, but it's actually like just using this. If you apply it to nearest neighbor, you can actually advance quite a bit. Or to like alpha nearest neighbor paths. You can probably like go from like 1,700,000 to like 1,650,000 or something. Like even this simple heuristic is enough to improve it quite a lot. So when k is greater than 2, then it becomes pretty hard to implement the general heuristic for that, because how do you choose those k edges? So a lot of the algorithms, they just use a sequential KOpt, which means that you choose a random edge that for some reason you don't like, and you replace it with a different edge from one of those 2 affected vertices, which now have 1 because you removed 1 from both of them, to a different vertex based on either nearest or alpha nearness. And then that would result in a new vertex that has 3 edges. So you remove one of those, that leaves another vertex with 1 edge. And then you just keep doing that, essentially. From that, you choose another one that based on nearness or alpha nearness. And then you have one with 3 edges, and then you remove one from there. And you have all different combinations how you can do it. And basically, at some point, obviously, you're not going to do it forever. At some point, you'll just go to the original one that just has 1 left from the first edge that you removed. So that's the sequential KOpt. And some people have done it in their solutions up to k equals like 20 or something like that. Obviously, they didn't exhaust all possible combinations, but they tried some of them. There is also a non-sequential KOpt, which is actually quite important for solving this problem. Here is an example of a non-sequential KOpt. The reason why they're important is because the good thing about non-sequential KOpts is that they don't require that all points are close to each other. For example, in this picture, when you do this change from the left to the right, the point on the left has to be close to the point on the right, and the point on the top has to be close to the point on the bottom. But the points on the left and right do not in any way have to be close to the points on the top and bottom. So, I mean, like the way a very effective version of this non-sequential KOpt is basically you choose 4 cities on your current path. You choose city number 1, 2, 3, and 4, such as that 1 is close to 3 and 2 is close to 4. And then you go all the way up to 1. Then you take all of the cities from 3 to 4. Then you take all of the cities from 2 to 3. And then you take all of the cities from 1 to 2. And then you proceed with the cities after 4. This way, 1 has to be close to 3 and 2 has to be close to 4. But if you connect them, you'll see that like there is no reason why 1 has to be close to 2 or 4 or 3 has to be close to 2 or 4. Yeah, so those non-sequential KOpts are actually like, they improved my solution a lot when I used them. Now I'm getting to some approaches that I didn't implement, but the top winners did. Yeah, one thing, like the biggest problem for me was that I was having a really hard time escaping local minima, because in any optimization problem, there is a good chance that you end up in a local minimum after a while. And in this problem, it seems like there are a lot of those local minima. So sometimes you need to make moves that worsen the true length and then optimize again and hope that the result is going to be better than what you started with. But you need a smart procedure of how to do that, and I just didn't have enough time to implement that. So yeah, I'm citing those papers there. So like if you're interested in the traveling salesman problem, you can go and read some of those papers, and they'll tell you about how to do those things. But actually, there are so many papers on travel and salesman problems. It's actually like you could probably spend like a couple of months just reading those papers if you got really interested. And there are books as well. And there is another approach that I haven't tried. Well, actually, I have tried that, but not to the point of like genetic algorithms that some people used. I used a little bit of the first one. Basically, the idea is to find segments in the tours. Like when you generate several good tours, if you have some randomness in your generation, like if you start with like random starting points, for example, or you have some randomness in your algorithm, then chances are you'll end up with two completely different tours. But the idea is to merge tours by finding the segments that start and end in the same cities and have the same cities in between. Then you just pick the one that is better than the other, and then you combine all of those segments to produce a better tour. That's how like the first algorithms essentially work, although there might be some little details there. And actually, what one of the winners did was, and several other people tried as well, I think, but for one of them it worked really well, is to use those genetic algorithms based on the paper that I'm citing there, and it's called edge assembly crossover. So basically, not only you're looking for those segments, but you're actually sometimes include mutations, edges that are not present in the parent, because I mean, like in the other algorithms, you are basically just choosing the better of the two paths. But here you're actually looking at possibilities that were not originally present. And I'm not an expert on genetic algorithms, so I'm not sure exactly how that works. But apparently, like if you really figure out how to implement that, that was a very effective approach. Another trick that a lot of people came, not a lot, but several like top winners came up with was to gradually reduce the penalty. So instead, what they did is, instead of just optimizing with the 10% penalty right away, they first took like a 1% penalty and optimized the path to that. Then they increased it to 2%, 3%, and so on. And I took this picture from one of the kernels for this competition. And it just shows you that when you increase the penalty slowly, instead of just jumping to 0.1, jumping to 0.1 are the green points. And basically, it just shows you the distance without penalty for the x-axis and the penalty for the y-axis. And you can see that as you reduce the penalty, you're making, for the green points, you're making the total distance without the prime penalty much worse. So you're basically getting to a much worse path in terms of like just pure TSP without the prime penalty. But if you do it slowly, if you slowly increase that penalty, then actually you achieve much better solutions. That's another thing that I haven't done. It just never occurred to me, but actually this is a pretty good idea. And it worked for people who tried it, or for most people who tried it.
Can you explain the dotted lines?
The dotted lines, I actually haven't looked at them, but let me see what that would be. I mean, so basically, I guess the dotted lines are basically if you reduce the penalty by a certain amount, they're all parallel to each other. How much you would increase the distance?
Like some bounding.
Yes, some.
Lower bounds.
Yeah, I'm not sure. I guess, yeah, I guess those basically just show you, like if the line approaches one of those, like if you look at different paths, like at different solutions, if the line is closer to the bottom or to the left, then it means that it's a better solution, essentially.
So I'm having trouble interpreting this graph that on the y-axis it's labeled penalty.
Yeah, penalty, the prime penalty, the additional number that you add to the Euclidean distance path.
So isn't the penalty going to be like 0.1?
It's 0.1 of the sum of all of those distances.
So this is the amount of the distance that is attributable to the penalty?
Yes.
Okay, thank you.
Yes, and as you can see, the base distance is on the x-axis, so if you multiply that by about 1%, 10% times 10%, then you get about the scale that you have on the other axis. So
I was just going to say I think those dashed lines represent equally good solutions.
yes,
Yeah.
yes, that's what I said. So like the more it is to the left or to the bottom, the better your solution is.
Right, but so that black dashed line on the top, any solution that falls anywhere on that line is like equally good in terms of the
Well, that touches that line, like
yeah, on that line, yeah.
yeah. So basically, like you want to touch, like to make your solution as best as possible, you need to touch the lowest of those lines. So yeah. Yes.
I'm just wondering, what is the dimensionality of this problem?
There's no dimensionality.
There's no dimension at all.
Well, I
So
mean,
I'm just wondering
you
how
can assign any dimensionality you want. I mean, you can say it's meters or kilometers.
No. Not what are the units? What's the dimensionality of the problem?
Or the number of cities?
Is that just the dimension there?
But
So we're in 200.
about 200,000, 197,768.
But we have a sequence.
You have what?
We have
a
a
sequence of
sequence.
those 197,768 cities.
Right, okay.
Plus the zero city that you start.
Twice. Plus the zero city twice, though. Because you've
Twice,
because you've got
twice.
to go
So
back to it.
yeah, 197,770 with visiting that city twice. Yes. All right. So since a lot of people on Kaggle are machine learning people, definitely some of them tried machine learning approaches. But I mean, I included some links to some possible approaches to TSP using machine learning, but none of them seem to really work well for a problem of this size, because most of them are sort of using some sort of local, like heuristics or whatever, like, and when you have a problem this big, sometimes you have to look very far ahead in terms of what your path is going to do in the future. So yeah, so machine learning, I don't know, maybe at some point in the future, someone will come up with an effective machine learning algorithm for TSP of a large size. But right now, it seems like it's not really a good way to approach those problems. So in terms of performance optimization, most winners used fast languages. Most use C++. The second place team used Rust, which is apparently about as fast as C++. I've heard the name of this language, but I wasn't really familiar with it. I didn't know that it was this fast, but apparently it is. A lot of people used Python because I guess that's the language they felt comfortable with, because like most people on Kaggle are machine learning people. In Python, it's quite a bit slower than C++ and Rust, I'm assuming, as well. Also, Python is not multi-threaded, so basically it's pretty hard to make it multi-threaded. So the way I did it was by just running different processes. So like I had 24 cores available for this, so I was just running like 24 different processes. Yes.
I have a question. How did you parallelize your solution? How did you split it up? Different cities. Is it by like cities? Like you grouped different cities on different cores. How did you share the work?
How did I share it? Basically, well, in my case, it was pretty simple. I mean, I used a little bit like, it happens sometimes that two different processes found the same solution. I mean, two different improvements to the same solution. So I had a procedure that sort of used something like this to incorporate both of them into one. But most of the time, basically, I just had another process that ran, and like whenever one of those would save a new solution, I mean, actually, the process that I had was just notifying me that the new solution was discovered. But actually, basically, all of those 24 processes, if they haven't found any improvement every like couple of minutes, they just read the solution, like the optimal solution that was saved by another process. Like, so each process, when they would find a solution, they would just save it.
Okay, so I understand what you mean now. So you split it by different like algorithms. So the same data through all the processes.
Yeah, so all of the processes, each of them was trying to optimize a certain, like either certain part of the path, like starting from a certain city in terms of those KOpt heuristics. Yeah, like obviously for optimization, you don't want to repeat the same work.
And is it like a reasonably rare event that one of your processes discovers an improvement?
Yes, at some point, like at first it was pretty fast. Like when you're applying like a new technique that you haven't applied yet, then you get like an improvement like maybe every half a minute or something, or every minute. But then you could wait for like an hour or an hour and a half to discover another improvement. And especially since I didn't have a good way to, like, first of all, my stuff was in Python, which was quite a bit slower than C++. And second, I didn't have a good way to get out of the local optima. So yeah, like for a while I would go, and then it would just stop finding any improvements because I would be in one of those local optima. And then I would figure out how to get out of it, but it was pretty slow. I didn't have an automated way of getting out of those local optima. Yes?
So you mean that your algorithm was greedy? You were only accepting moves that improve your score?
Yes. Yes, my algorithm was greedy because I couldn't figure. I tried to figure out how to make it non-greedy, but I didn't have enough time to actually implement it somehow in a smart way. Because obviously I don't want to accept like every step that leads me the wrong way. I need to somehow do it efficiently so that I check whether I can move into a better solution. And yeah, I didn't implement that fully. Yeah, another thing that people used is this module for Python that is called Numba. And basically, it translates Python code into optimized machine code. And like, it depends on what you apply it to. Basically, if you have code that has already been highly optimized using some NumPy arrays, then it's not going to give you, like, it might actually make it even a little worse. But if you have something like this procedure here, then it runs about 30 times faster when you just put this decorator there. When you import Numba and just put that decorator. So yeah, like if you're doing something that you cannot easily put into NumPy, then this could be a great way to improve the performance of your Python code. All right, so now I'll move on to winner's solutions. Okay, the first place solution, they never posted a write-up. So the only thing that was available is their public kernel without any explanations. I kind of had to go through the code of that kernel and see what it does. So basically, I mean, it's possible that maybe they did something in their actual winning solution that they didn't do in this kernel, because the score of this was, the final score of this kernel was 1514,325, and their actual solution was 1513,747. So maybe they had some more tricks that they didn't want to share, or just they wouldn't be fast enough to run them in the kernel. But basically, they first did pure TSP, And they divided the problem into 5 sub-problems because apparently for some reason it worked better. I guess they're the world-leading experts, so they know what they're doing. So, and then they coded the prime penalty into their C++ code, and they ran that, which got them already to noticeably better than my score. And probably that score of the second step in the kernel would already get them close to the top 10 there. And then they kept breaking the tour into small sub-problems and optimize each separately using the same solver with prime. But the difference is that it was not connecting back to the original city because they were looking at sub-problems. And that got them to already really good score that would have been in the top 5 or something. And then they made some small improvements. But that's, as I said, this is the kernel solution. So maybe in their actual solution they did something else, but it wasn't available, so I don't know. Okay, so the second team called Farmers Peen Further. Yeah, those guys, they actually won this kind of competition, also travel and salesman problem, but with a different twist a few years ago. So they were quite familiar with it. And actually they, from the beginning of the competition, they were in first place for a while. And then after about maybe 10 days, those other guys joined. And then they were in the second place for the rest of the competition. But these guys really know what they're doing. Yeah, they've participated in several of those before, and they won at least one of them, maybe even more than one, I'm not sure. So they, as everybody else, they started with pure TSP, with LKH, and then they discovered this trick of slowly increasing the penalty, not just jumping to 10% right away, but going 1%, 2%, and so on. And then they used those kicks. So basically, some moves that temporarily increase the score, and then optimization to decrease it more. And here is I listed what they did, according to their description, several 8-op moves that do not increase length by more than 20, and then optimize, or alter the penalty a little bit, either up or down, and then optimize, and then go back to the penalty that they. So that seemed to work for them. And fourth is what I said, basically creating different solutions and then choosing the best parts of them. And I mean, that got them to second place according to their description. So I don't think they I'm not sure, maybe they even posted the code. Yeah, I think they actually posted the code on GitHub. Yeah, so if you're interested and if you know Rust, you could go and look it up. Okay, so the third place solution, sort of more of the same, pure TSP first, and then this guy also incorporated the penalty into the code of Lynn Kernighan. And then he tried applying higher opts up to more than 20 opt. And then, as you can see, using those kicks and re-optimizing, he achieved a lot of progress there. And then once again, using different solutions and recombining them, using a slightly different approach from the other guys, but also finding the best of several solutions that worked for the third place. The fifth place guy was the guy who actually, he wasn't even anywhere close to the top places until about the last day or two. And then everyone among the leaders got scared. They were actually commenting about it in the kernels because he started improving so fast. Because he encoded those genetic algorithms. So he basically did everything the other guys did. And that got him to 1514977, which is where most people got stuck, those who were close to the leaders. And then he discovered those genetic algorithms and got into fifth place. And maybe if he had another couple of days, I mean, maybe he could actually compete for the top 3 there. Okay, also 8th place solution was posted. I mean, it's sort of more of the same pure LKH, then those different opts, and then kicks. And then these guys tried the genetic algorithms, the same ones, but they didn't result in great improvement for them. So I guess it was a different implementation. So it might not be so easy to implement those. And then they use something else, shuffle cities on segments up to 200 using lower bound estimation. I'm not sure exactly what it is, but some kind of a mathematical trick that actually got them a noticeable improvement. And then they just used more and more of those different methods, and like that got them to the 8th place. Well, here's my solution. So also pure LKH, then 2 and 3 opts, then non-sequential 4 opt, then 5 opt, local permutations, combining solutions, running more optimization. But as I said, I never got those kicks working. So if I did, maybe I would have gotten a better score. But it was good enough for 47th place, which is not too bad, I suppose. I got a silver medal, so I'm an expert on Kaggle now. If I get another gold medal, then I'll be a master. But I need to work towards that. Yeah, so what I could do better is use C++ instead of Python, but since I have a job, I didn't really have time to refresh my knowledge of C++. I used it like 15 years ago the last time, so. And also, like, I was trying to figure out most things for myself first, like if I just read all of those papers and then started programming, maybe I would have done better, I don't know. A couple of other approaches that people used, like this 36th place team used something called integer linear programming, and it seemed to work for them. Many teams tried simulated annealing, but no one said that it really worked well for them. So, well, and that's everything that I had to say about this. So if you have any questions. Yes, Adrian?
A couple of questions. Okay. Hello? Yes, a couple of questions. First, the difference between different of your solutions, is it really substantial?
Between which solutions?
Like you listed several of your solutions.
Like the score for my solutions?
Yeah. The difference in scores, is it substantial?
Relative to what?
Like, is it noticeable in running time or like?
What do you mean in running time? Like I did the first thing first, like the pure LKH. That got me to 1.5.16.390. For that, I didn't write any of my own code. I just ran the existing LKH solver for about 6 hours, 10 hours, something like that, and I got that. And then I used those 2 and 3 opts, which, like, with the code that I had in the end, like, I could probably do in another, like, 5 or 6 hours, and that would get me from 5.16.390 to 1.5.15.900 something. And then the non-sequential 4 opt, which is another day or two to run, got me to 5.15.600 something, and then 5 opt in another few days, like 1.5.15.400 something, and then combining solution and like trying all of those tricks all over again. Basically got me to the final score. So like all of the numbers are there, so I'm not quite sure if I understand like the question about substantial.
And one more question. If like here prime cities are distributed more or less uniformly.
Yes.
If that was not the case, if there was clustering, like for instance prime twins, would it substantially affect the solutions, the algorithms?
The algorithms probably not. I mean, basically, since the prime penalty is so small, it would just mean that basically you will be very close to the pure TSP path if all of the prime cities were on one side and all of the non-prime cities were on the other. You would maybe make some small changes, but it would essentially not be a very interesting problem because you would just use pure TSP and then you would improve it like a really tiny bit. because obviously you cannot get many of prime cities into those 10th positions if they're not uniformly distributed. So yeah, I mean, I think, but if you make the prime penalty really large, then it would become like an interesting problem. Then what do? Do you like keep jumping there and then out of there, or yeah, like if you had those prime cities in a cluster somewhere, then you would probably really need to increase the prime penalty to make this problem more interesting.
Those improvements in your score as we progress, do those generally represent like many small improvements or like fewer, rarer, large improvements?
No, they represent small improvements. I think like in terms of those opt moves, the largest improvement that I ever got was something about 8 or 9. So like to get an improvement of a couple hundred. And most of those were, I mean, I got a lot of improvements that were like 0.01 and stuff like that, so.
Do most people use local machines or cloud?
Well, I haven't collected any statistics on that. I would imagine that there is a split. I mean, like basically, I mean, a lot of people actually like who don't have very powerful computers just use the Kaggle kernels for that. So basically, they just ran it in the kernel. And I mean, I'm like the second place team, for example, they were talking about 72 and 48 core machines. I mean, they would have to be like really professional Kagglers to like have this kind of software at home. I don't know, but maybe they are, and maybe they. I mean, on the cloud you can. I guess on AWS you can get up to like 768 or some cores. I'm not sure what the exact number is, but yeah, you can get a lot if you're willing to pay the money.
Okay, awesome. Thanks, Dan. That was great.
Thank you.